Well, we now see Green's theorem in the plane, and we will give a statement without proof. It is very easy to remember the theorem. It states that if we take a closed contour that is going to be called C, and that will be specified in the Cartesian plane, and take the contour integral for this combination of functions P with respect to x and Q with respect to y, that can be converted to over R. I will explain what is R. The double integral of del Q del x minus del P del y dx dy. So we will use the properties of double integrals. We will set the limits. Now this R is the region in the Cartesian plane that is enclosed by C. So here, for example, I'll just try to take an example. If this is the closed contour C and it is going to be traversed anti-clockwise, the direction of traverse is indicated. Even here we have seen that the closed contour, the symbol is that we're going to take a closed contour and we're going to traverse it in the anti-clockwise direction. If we put it clockwise, then the entire sign will be changed, nothing else will happen. So if this is minus 2, then if we take the integration clockwise, it will become plus 2, nothing else. Now P is a function of x and y, and Q is also a function of x and y, including of course special cases in which one or both may be constants. But we will of course not tackle such special cases. We will take an example in which the contour C will be specified, and as I was saying, the region R is what is falling inside the closed contour. That is the region R here. So again repeat, the closed contour integral over C that is specified of P dx plus Q dy, where P and Q are functions of x and y each, is nothing but the double integral of del Q del x minus del P del y evaluated over the region R, where R is the region in the Cartesian plane that is enclosed by the closed contour C. So we will take an example and see how the theorem works. Let's see. We will take very simple cases, because to understand the theorem, the best way is to verify through a very simple case. Later on, complicated functions can of course be tackled, but the spirit of the theorem will not get lost by taking simple instances or simple expressions for the values of P and Q. We now take an example to verify. Actually, this is not a proof, it's a verification of Green's theorem, which we have just stated, and we would like to state the problem in detail so that the later on workings will be easier understood. Otherwise it gets complex. Now we had seen that we were trying to take the contour integral anti-clockwise, and this was converted to a double integral over a region R. R is the region that is enclosed by the closed contour C. We've just seen that, and it is significant that we are going around the contour in an anti-clockwise direction. That is by convention. We can always go the other way around, but the sign will change, as we just said. Now we have taken simple functions. Pxy is x plus y, qxy is x minus y, and the closed contour C is defined to be this contour starting from the origin, going to the point 1, 0, then from the point 1, 0 going up to the point 1, 1, and from 1, 1 getting back to 0, 0 via the line y is equal to x. So this is the definition of the closed contour, and evidently therefore the region that we call R is this one, which I will just shade. So we will see by taking these values whether the line integral over a closed contour is actually equal to the double integral for the same functions, and we remind ourselves that the double integral is of del q del x minus del p del y dx dy. So first let's start by evaluating this contour integral. We will evaluate in steps. First of all, we'll take the line integral of p dx plus q dy along C1, then along C2, and then along C3. We will do that in small steps, otherwise chances are that errors will be introduced if we are in a hurry. First is step 1. Value of integral p dx plus q dy on C1. So C1, as we said, is the line merging with the x-axis and going from 0, 0 up to 1, 0. Now this is nothing but p is x plus y dx, q is x minus y dy over C1. Now on C1 we can see y is equal to 0, and the limits for x are from 0 to 1. So we write that as on C1 integral x plus 0 dx plus x minus 0 dy. Now one thing very significant is that this part will vanish because on the curve C1 there is no variation of y. So dy is 0 since y is 0. So this integral just vanishes. So we are left with an integral x plus 0 dx, and the limits on C1 are for x is equal to 0 to x is equal to 1. So 0 to 1, this is nothing but x square by 2, 0 to 1, and that is equal to half. We will capture this value. So p dx plus q dy on C1 is equal to half. First value captured. Similarly, let's go to the integration of p dx plus q dy over C2, that is the vertical line that rises from the point 1, 0 and goes up to 1, 1. So we will do the value of p dx plus q dy on C2, and this becomes now step 2. Again, we'll change this to C2, rub this part out because this will certainly change. So on C2 we have, what do we have? On C2 we can replace x with 1 because x has a constant value of 1. Y varies from 0 to 1, but x is 1, and y varies from 0 to 1. And we notice that because x is constant, dx is 0. So the first part of the integral will vanish anyway because there is no change in the value of x. So dx is 0, and all we are left with is 1 minus y dy, and y varying from 0 to 1. So this reduces to 0 to 1, x is 1 minus y dy. Now this can be integrated to y minus y square by 2, limits 0 to 1. So again we get half. So I don't think there's anything wrong there. 1 minus y and dx is 0 because this line has a constant value of x. No change in the value of x means dx is 0. And x minus y is changed to 1 minus y integrated with respect to y, and the limits for y are 0 to 1. That's perfectly all right. So we capture that result as well and write over C2 the value is again half. Step 3. So that's going to be evaluating P dx plus Q dy on C3. And our step 2 now becomes step 3. Observation on C3. Y is equal to x. Y is equal to x. This is the equation of this line. And x and y are both changing. So neither dx nor dy is going to be 0. But x is equal to y. So let us see what happens. Integral x plus y dx plus x minus y dy on C3. Now very simply this term will vanish because on C3 y is equal to x, so this will just be annihilated. This integral will just not be there. So all we are left with is x plus y dx. Now this does not create much of a problem because on this curve y is equal to x. So dy and dx are the same, or we can write this y will replace by x. So we will get nothing but x plus x, that is 2x integrated with respect to x. Now what are the limits for x? One has to be very careful here because we are traveling from point 11 to point 00. So the limit for x is equal to 1 to x is equal to 0. Not x is equal to 0 to x is equal to 1, because the direction of traverse is like this, anti-clockwise. So we write x is equal to 1 to x is equal to 0. Now this is x squared from 1 to 0. So this is 0 minus 1 minus 1. C3, the value is minus 1. So if we add these three integral values, we get a result of 0 for the contour integration of this particular combination of P and Q. So we will just record that the contour integral value, closed contour integral value for this particular case is 0. We keep it here. Then proceed to find the value of del Q del X minus del P del Y over the region R.